Well, thanks, Chris, for the nice introduction. I'll be presenting generalized parallel tempering for Bayesian inverse problems. This is joint work with Professor Fabio Nobile at EPFL, with Professor Raul Tempone at RVTH Aachen and KAUST, and with Professor Jonas Latz at Heriot-Watt University. Okay, so what is a Bayesian inverse problem? Well, given some measured data y that we can model as y equals f of u plus e, where u is a set of random parameters with known distribution mu prior, f is a mathematical model of the physical process that generated the data. It can be understood as a forward mapping from a parameter space x to a data space y, and e is some random noise with known distribution mu noise. The goal of a Bayesian inverse problem is to sample this set of unknown parameters u conditioned on this measured data y from a posterior distribution mu y that we can write as likelihood times prior, where the likelihood sort of measures the misfit between y and f evaluated at u, and the prior encodes the information that we have about u before any data has been observed. More commonly, this is written in terms of the Radon-Nikodym derivative of the posterior with respect to the prior, given by this term here, where more often than not, this potential depends only on this misfit y minus f of u, depends on the choice of noise model, but for simplicity, let's assume that it has this form, and z is just a normalization constant such that this integrates to 1. There's a caveat here, and it is that we want to sample from this posterior distribution, but we cannot do it directly, and usually we need to use Markov chain Monte Carlo methods to do so. So the idea behind MCMC methods is to construct a Markov chain whose invariant distribution is mu y, the posterior that we want to ultimately sample from. And perhaps the best known Markov chain Monte Carlo algorithm is the Metropolis Hastings algorithm that works by iterating the following 2 steps. One first samples a candidate state set from a proposal distribution Q that we assume that it's a probability distribution that we know how to sample from. And typically, or in most cases, this probability distribution Q depends on the current state of the chain. So you can think of it as a Gaussian centered at UN. And once this candidate state set has been sampled, we accept it or reject it as the new state of the chain with probability alpha UN set. If we accept it, then fine, it becomes the next state of the chain. Otherwise, we reject it and we set UN plus 1 equal to UN, so the current state. What's important to mention here or to notice here is that to evaluate this accept reject probability, we need to evaluate the posterior density at each new candidate state, and which in turn implies that we need to evaluate this mathematical model of the physical process that generated the data, which can in turn become quite expensive if we do this many times. Okay, in short, and just to introduce some notation, this procedure induces a Markov transition kernel P that can be understood as sort of a measure that depends on the current state of the chain UN, and from which we sample the next state UN plus 1. Okay. Once a sufficiently long chain has been obtained, we can estimate posterior expectations of some given quantity of interest Q of I with the usual ergodic estimator based from the samples obtained from this algorithm. Now, there is an issue here, and it is that typically this proposal distribution Q is a localized proposal. So sort of like a Gaussian centered at the current state of the chain, which is the case for Random Walk Metropolis or PCN. And these type of proposals tend to struggle a bit when the posterior is very difficult to explore. So basically meaning when it sort of concentrates around the lower dimensional nonlinear manifold, or when the posterior is multimodal. Since they tend to struggle for these sort of posteriors, they usually require many samples to explore it in its entirety, and which in turn implies that we would need to obtain a very large number of samples to compute this quantity of interest at a acceptable accuracy. And since we need a very large number of samples, the whole cost associated to this algorithm can become prohibitively large. So just to show the drawbacks of using sort of localized proposals, which again are the most common type of proposals, if we consider, say, a random walk metropolis type of proposal, so a Gaussian center at the current state of the chain, and we have these sort of pathological posteriors, we can see that the chain really struggles at exploring the distribution in both cases. So here it either has to take very small steps to keep in the region of hyperability given by this blue curve, or if it takes larger steps, then it's quite likely that it's going to fall off the region of hyperability. If we look at this multimodal case, it either takes very small steps, in which case it's going to be very unlikely that it's going to jump from this mode to this mode, or it takes larger steps, and again, it will reject too much, and that is not something that we want to do. And in either case, this is an artifact of this posterior being very concentrated around either this nonlinear lower dimensional manifold or around each of its modes. So what if we inflated this posterior? Well, if we introduce an inflation parameter t bigger than 1 that we call the tempering parameter, that essentially it just divides the argument here in the potential. By introducing this, we would have a posterior distribution that is sort of flatter, that kind of resembles the one that we had before, but it's a bit wider. And as such, it will be easier to explore for these sort of localized proposals, right? However, there's one technicality here, and it is that this posterior is obviously not the one that we were ultimately interested on. So what is the idea behind tempering methods is to take advantage of this inflation of the posterior, but at the same time producing samples that come from the right distribution, from the distribution that we're ultimately interested in. Okay, so let's introduce some notation. So we introduce a set of capital K temperatures ranging from T1 equals 1 to possibly Tk equals infinity. We introduce a joint posterior mu y bold as this product of posteriors, mu y1, product mu y2, all the way through mu yk. We define mu yi, each of these posteriors, essentially in the same form, likelihood times prior. However, here we have this temperature parameter that divides the argument of the posterior. And we introduce this joint state u bold as the state having components u1, u2, all the way through uk. Again, here the idea behind introducing these tempering parameters is that as t grows higher and higher, the density associated to mu yi becomes flatter and flatter, as you can see here. So for temperature 1, we have very well separated peaks, and as we increase the temperature, the density becomes flatter and flatter, and as such, it becomes much easier to explore with a localized type of proposal. Okay, so what is the idea here? Well, instead of sampling from just mu y1, we sample from this joint measure mu y bold, which again is this product of measures here, using a joint Markov transition kernel p bold in such a way that from mu1 we sample using a Markov transition kernel p1, from mu2 we sample using p2, all the way through mu k, which we sample from using this Markov transition kernel pk. So we evolve all these k chains in parallel using their own Markov transition kernel, meaning like its own random walk metropolis with some given step size. However, up until here, we haven't done anything too interesting because we're just running multiple chains in parallel. But then the idea behind these tempering techniques is to introduce a swapping kernel Q that is invariant with respect to the posterior that we're with respect to the joint posterior mu y bold, sorry, in such a way that the swapping kernel mixes the states between these chains that we're running in parallel. So perhaps a bit graphically, if we consider just two chains, this idea of combining this joint kernel, these kernels P and Q looks as follows. So we evolve both chains in parallel, and every so often we propose to swap states with the swapping kernel Q. The swap can get rejected, nothing happens, or it can get accepted, and if it does, then the chains swap states, and as such, it will be easier for the chains to explore the whole posterior distribution. Perhaps the most commonly known or the best known tempering algorithm is what's called the classical parallel tempering, which works as follows. So we are at a current state un. We evolve or we advance each of these components with a step of, say, random walk metropolis or PCN. We get an intermediate state u tilde. And to the components of these u tilde, we attempt to swap states at two at continuous temperature, so states at temperature 1, 2, 2, 3, 3, 4, and so on. This attempt of swapping gets accepted or rejected with the usual Metropolis Hastings accept reject step, and this would give us the next state of the chain. However, this approach is not necessarily optimal in the sense that the chains that you attempt to swap are chosen a priori. Now, motivated by the infinite swapping algorithm, which is a molecular dynamics counterpart of the parallel tempering algorithms that can be understood as a continuous time Markov-Jump process where swaps happen infinitely often, and that can be shown to be computationally more efficient than the continuous time parallel tempering method for molecular dynamics, we introduced three things. The first one is a generalized swapping kernel that can account for not only the case where you fix which temperatures you want to sample, which chains you want to swap a priori, but for any sort of swap that you might think of. And we introduced two algorithms that aim at replicating what this infinite swapping algorithm does. The first one we call unweighted generalized parallel tempering, for which we create a parallel tempering algorithm that accepts swaps at every step. And the second one is called the weighted generalized parallel tempering algorithm that takes the physical intuition behind this method, which is that instead of when these chains swap states infinitely often, the physical interpretation is that they're not swapping states, but they're swapping their dynamics, like the temperature and the amount of, like the size of the steps that they can take. So in this weighted generalized parallel tempering method, we aim at replicating these physical interpretation. Okay, so let's introduce a little bit of notation with a node by bar sk, the collection of all k factorial permutations of this set from 1 through k. We define a subset sk from bar sk as a subset that satisfies that if a permutation sigma is in sk, the inverse permutation sigma inverse is also in sk. We denote the cardinality of sk by this number with bars. We define the swap state u sigma as the state with swap components. So for example, if I have three chains and my joint state is u1, u2, u3 before the swap, then the swap and my permutation sigma is 3, 1, 2. So the one that puts the last component first, the first component second, and the second component last. My u sigma has the form u3, u1, u2, which in turn means that, and we also define, these joint posterior measure or joint posterior density mu y evaluated at u sigma as each component of this posterior density evaluated at the permuted state. Furthermore, we define the swapping ratio R u sigma that can be understood as the probability of drawing a permutation sigma from this set of permutations sk given a state u. And given this, we can introduce the following procedure. We sample a permutation sigma from this probability from this kernel Ru. We generate a permuted state U sigma, and then we accept U sigma as the new state of a chain or the chain with a probability alpha swap, which is given by the usual Metropolis Hastings accept reject probability. Otherwise, if we don't accept that swap, we stay at U. Okay, so by considering these three steps, we induce a swapping kernel Q that both mixes the components of the state U while at the same time preserving this distribution Y. Okay, so touching up on the algorithms, the unweighted generalized parallel tempering case, the idea here is to construct a kernel that always accepts. And to do so, if we define RUW, this probability of sampling a permutation given a state in this form, we can easily see that the accept reject probability is always 1. So the way that we induce this swapping kernel on the unweighted generalized parallel tempering case is fairly simple. We sample a permutation we sample a permutation sigma from this kernel RUW evaluated at U. And then we permute the states and we accept that permutation with probability 1. Having defined this swapping kernel QUW, we can define our generalized unweighted parallel tempering algorithm as follows. So with this palindromic structure, which basically means that given an initial state un, we first permute the states with a permutation sigma. We accept this permutation with probability 1. We get this intermediate state u sigma 1 all the way through u sigma k. To this intermediate state, we apply one step of our favorite kernel P. So like Random Walk Metropolis PCN on each component. We get another intermediate state u tilde. And to this intermediate state, we swap the components with an additional permutation rho sampled from our UW of evaluated at this intermediate state here. And once we have done these three steps, QPQ, we get our next state of the chain, UN plus 1. For the weighted generalized parallel tempering case, where the intuition is that we want to sort of swap the dynamics of the chains, we need to introduce a little bit more notation. So we define P sigma U as this product of permuted Markov transition kernels P. We define mu y sigma U as this joint measure with the permuted temperatures. So it's a bit different from mu y of U sigma. And we define these weight W sigma U as follows. And having introduced these three things, we can define our weighted generalized parallel tempering PWU as this convex combination of kernels, which induces a fairly simple algorithm. We sample a permutation sigma from a probability proportional to, well, the probability given by this W sigma. And once we have sampled that permutation, we sample the next state of the chain UN plus 1 from a Markov transition kernel P sigma, so from this permuted kernel here. And again, this can be understood as a swap of dynamics, meaning that you're swapping the temperatures and the kernels, so like the step sizes of a random walk metropolis, if that's what you're considering. So again, perhaps to illustrate it a bit more graphically, if we consider just two chains, one that has like low dynamics, so that's taking very small steps, and one that's taking very large steps, whenever a new permutation sigma is swapped, then the chain that was taking very small steps starts taking very large steps, and the opposite happens for the chain that was taking very large steps. It starts taking very, very small steps. Now, I should mention that this procedure, or this Markov transition kernel PW, is not invariant with respect to mu y bold, but it is invariant with respect to this sort of symmetrized measure. Okay, so this implies that if we want to compute expectations of quantities of interest, we have to do it via importance sampling. So if we define our quantity of interest of the joint state to just be a quantity of interest with respect to the first variable, then we can write this posterior expectation here. This is the posterior that we're ultimately interested on, as this expectation with respect to the joint posterior of just the first quantity. If we do the usual change of measure trick from importance sampling, we would get something that looks like this. And since this is invariant with respect to permutation, we can write it on this form, which we can approximate with this ergodic estimator, where here these 1 over cardinality of sk times n terms appear, which kind of gives the impression that you would get a factor of cardinality of sk improvement. However, it's important to mention that these are cardinality of sk times n weighted samples, so it's not that you get that much improvement, but you do get some improvement computation. Okay, so touching up a bit on the theoretical results. So informally, if we assume that for each chain, that each Markov transition kernel Pi is reversible with respect to mu yi and geometrically ergodic with some rate ai, and that for any two permuted joint measures mu sigma and mu rho, the overlap between these joint measures is strictly larger than 0. And then we have that for all r in 1 through infinity, The unweighted generalized parallel tempering algorithm is reversible with respect to mu I bold and geometrically ergodic with a rate that is the maximum of the rates, and that the weighted generalized parallel tempering algorithm is reversible with respect to this symmetrized measure mu I W. And again, geometrically ergodic with it converges to such a measure with geometric ergodicity with a rate that is given by the maximum of the rates. So informally, what this result says is that by doing these tempering techniques, you don't perform worse than the worst performing chain, you don't screw up. But experimentally, we have seen that these tempering approaches can lead to very large improvements in efficiency. So just a bit of a sketch of this proof. So the first part is that if PUW is mu I bold reversible, is mu I bold reversible and geometrically ergodic with respect to such a measure. So to show this, we rely upon three assumptions. The first one is to show that Q bold is mu I reversible, which is fairly straightforward to do. Second one is that P bold is mu I bold reversible if each of its components is mu I reversible, which is straightforward but also a bit tedious. And the second proposition is to show that one can upper bound this operator norm here. So the operator norm of the joint Markov transition kernel P, one can upper bound it by the maximum of the operator norms of each individual Markov transition kernel. Based on these three propositions, then one can show this that is reversible and geometrically ergodic. Reversibility is relatively straightforward since we have this palindromic form of PUW. Then this means that PUW is reversible if both P and QW are reversible. So proposition 1 and 2. And ergodicity follows from the fact that P is geometrically ergodic if this operator norm is smaller than 1. And in fact, given this form, if we take the operator norm given by this, we can upper bound it by these two terms. Since Markov transition kernels are weak contractions, this is more than or equal to 1. And by proposition 3, this is smaller than 1 as well. For the convergence of the weighted generalized parallel tempering algorithm, we have a slightly trickier procedure. But again, we rely upon this proposition 2, where if P is reversible, each of its components are reversible, and on this technical bound on the variance of each with respect to each of the permuted joint measures mu I sigma. We needed to show that one can bound this variance in terms of the overlap between measures. And again, reversibility is straightforward from the definition of PW plus proposition 2. And ergodicity is much trickier, and it relies upon a technical bound on these operator norms in terms of this proposition 4 and the maximum, or the minimum between the spectral gaps of each operator. Okay, touching up on a key point about implementation, whether we're using the weighted generalized parallel tempering that has this form here for the probability distribution of the swaps, or the unweighted case which has this form, we need to compute cardinality of SK computations of U sigma. However, we can get away with doing this with only K, so the number of chains, computations of phi U. And depending on the number of chains, these might be the dominating cost, because every time you need to evaluate phi U, you need to solve a PDE, basically. And just to give an example, if we consider 3 chains and we consider all possible permutations, then for 2 given permutations sigma and rho, sigma 3, 1, 2, rho 2, 3, 1, we have as follows. If we want to compute this joint posterior mu I U, we need to evaluate this term here in blue, this term here in pink, and this term here in orange. But if we evaluate these 3 terms and we store their value, then we can compute mu y of U sigma, by just essentially taking these stored values and permuting the temperature, right? So we only need 3 re-evaluations of phi, which is which, depending on the regime where you are, is the expensive part. Okay, so for example, for moderate k, if the cost associated with this forward mathematical model is much larger than the cost of computing permutations, then it's worth taking all possible SK factorial permutations. So here I have a graph where here in purple is the cost of permutation, and here in red and in blue I have the cost of evaluating this forward mathematical model for two different forward models. As we can see that there are depending on the cost of f relative to the cost of permutations, it might make more sense to take all possible permutations or just take a subset of them. On the other hand, if k is very large, one needs to consider a smaller group of possible permutations, so it doesn't make much sense to consider all possible k factorial permutations. Or one could sample this permutation from, say, RUW using MCMC on this distribution, or rejection sampling or something like that, but that's something that we would need to explore in more detail in the future. Okay, so just to start finalizing, just on a numerical example, here we're interested in finding the probability distribution of the source location of an earthquake, given wave recordings in space of time. So we define a computational domain and a unit with and some domain for our domain for our parameters of interest given by U1, U2, U3, and U4, and we define our mu prior as a uniform in these in this set X given by this domain times these two intervals here, and we model our wave phenomena, our earthquake, in terms of this acoustic wave equation. Here we aim at estimating the posterior expectation of the source location, which has this sort of Gaussian form in the domain, based on some noise polluted data, where here we also include uncertainty in the material properties, as well as, of course, in the source location. So we generate here some synthetic data by solving this equation here with some predetermined values of U star and observing its solution at 3 receivers on the top boundary of the domain at 117 time instance, and polluting this observation by some additive Gaussian noise with about 2% signal to noise ratio. So having this, we can pose our Bayesian inverse problem as sampling from this posterior distribution that has a uniform prior and has a density given by this term here, where F again is the solution to this wave equation using a finite element method on a sufficiently small grid size and with a sufficiently small time step. And why is this a difficult problem? Well, the forward model is expensive, and the posterior has a very complicated structure. So again, since we're interested in finding the source, it concentrates around this region of high probability. But if we look at the rest of the posterior, so basically by fixing the material properties and plotting the posterior density versus source location, we can see that there are regions of high probability, so like these banana shapes here, that are enclosed by regions of relatively low probability. So if you're sampling this source location with, say, a random walk metropolis, and you start somewhere here, then it's going to be very unlikely that you will jump from, say, this point to this region with high concentration of probability. Furthermore, that picture was only for 2 fixed values of material properties. If we change the material properties as well, we can see that there is sort of this manifold here on the second component of the source location. So for one realization, the material properties, this region of high probability concentrates around the true source location, but for a different realization, it might concentrate below the source location or above, or so on and so forth. So they concentrate around this vertical manifold, which makes it even trickier to sample from. Okay, so we implement Random Walk Metropolis as a base method. So we just want temperature. We implement the vanilla parallel tempering algorithm plus our methods with 4 chains with temperatures given by 1, 738, 54, and 400. And we test our methods in terms of the variances of the estimators of the quantities of interest that we want to look at. So this is the expected value of the source over 100 independent simulations, each with about 2,800 PDE evaluations given by K times N. And the way that we choose to do this is K times N is so that the cost is comparable across all methods, right? So for example, for the Random Walk Metropolis, where K equals 1, then we do it with 2,800 evaluations. Meanwhile, in the case of parallel tempering and our algorithms, we do it for 4 chains, each having 7,000 samples. Okay, and if we compare our gains in terms of the variance of the basic method divided by the variance of the other algorithms, we obtain something that looks like this. So as we can see, in either case, we get about, I don't know, 2 orders of magnitude or even much more with respect to the base method. And we can also, like comparing to 2, let's say, competing methodologies, we can also see a factor of between several orders of magnitude to about twice as cheap. And in the paper, we also consider several other Bayesian inverse problems of varying dimensions, ranging from very low, from like 1-dimensional toy examples to very high of about 800 dimensions, yielding similar results, okay? Obtaining gains between twice sufficient to several orders of magnitude. Okay, so some conclusions, and to summarize, we propose 2 tempering approaches that can be understood as having self-tuning state-dependent proposals. Again, all of these methods are constructed on top of a base method, so they can be combined with fancier Markov translation kernels, such as Hamilton Monte Carlo, Amala, Dram, whatever. We presented, at least in the paper, a very thorough theoretical analysis. However, our numerical results suggest that theory can be improved in the sense that we still haven't captured the fact that experimentally this is much more efficient. And we've also presented a way of efficiently implementing this method by storing the values of these potentials, which sort of induces a guideline on the choice of the permutation set, or at least on the size of the permutation set. Some perspectives or some future work would be to refine the theoretical analysis of this method, to define a rigorous framework for the choice of the number of chains for the choice of SK for large case. And the third one, which I mentioned 2 weeks ago, was to combine these tempering approaches with multi-level Markov chain Monte Carlo, which is not necessarily trivial in the sense that it's not immediately obvious how should one couple, if one should couple these multi-level chains for just a temperature 1 or for all temperatures. Since these methods take big jumps, that is not necessarily something that you want to happen in a multi-level MCMC type of algorithm, because you might inflate the variance. So one needs to be extra careful with that. And to me, it's not immediately clear whether one can apply the trick of storing the values of this potential, since in this case, one would have that these potentials are indexed by both the temperature and the discretization level on a multi-level MCMC algorithm. So perhaps it's better suited for a multi-index type of ideas, but still needs to be discussed. And I think Rob will be presenting a multi-level MCMC tomorrow or so. Okay, so to main references here, this is our paper on statistics and computing. And this is this infinite swapping algorithm that I mentioned at the beginning. That's it. Thanks.